This first video is to go over how to find the domain of a few types of functions. So the domain is basically all of the input values or x values that are allowable for a certain type of function that will not cause that type of function to be undefined. All right, we're going to be able to put in something for x and get something out of it, the output value, the dependent value, the range value. So what values of x could possibly cause something to go wrong in an example set up like this one? There's a few things we need to pay attention to, and in order to warm us up, I'm going to start by going over a couple of these, and we'll take it from there, okay? Or actually, even before that, what if we even had something like this example? So I'm just going to write an extra one over here. Say I gave you something like f of x is equal to 1 over x. Which x value, all right, we're looking at the domain right now, which x value is bad, or which x values are good? Some people might right away realize that x cannot equal 0, and that's great, okay? You're not allowed to divide anything by 0. So that means that x is not allowed to equal 0. So you could either describe your domain by describing what values of x you cannot have, or you can describe your domain, I'm just going to use a capital D for domain, by all the values of x you can have. So sometimes we use interval notation and we say from negative infinity until 0 with a parenthesis. That means that 0 is not included. Then we might use this union symbol. Sorry, squeezing at the end of the page here. This union symbol, and I ran out of room, so I'm just going to go over here, and we'll pick it up right after 0 with the parenthesis, and we'll continue until positive infinity. So that's the way we might write something for an example like this one. Now, just to change this example a little bit, as easily as I can here, let's see. What if I made my denominator x minus 8? Now, sometimes people are like, oh, you can't divide by 0, so x can't equal 0, and they just jump to that right away. But you have to be a little bit more careful. Which x value will cause the denominator to equal 0? Some people look at it and they kind of do it in their head, and that's not always the best way. While it's great that you can get the right answer, it's not always the best way. You might see that x is not allowed to equal 8, and that's good if you can see it, but let's talk about how you do it. You basically take your denominator, which is x minus 8, and you establish the fact that x minus 8 can't equal 0. And from here you solve for x, so that means x can't equal, add 8 to both sides, 8. Okay? When it's linear, it's a lot easier. Here, same idea of a domain, we could still write from negative infinity until 8, and then from 8 until positive infinity. So this is writing your restrictions, and this is writing everything that's good. So maybe your parents are like, you can hang out with everyone except number 8. And you're like, what? If I can't hang out with 8, who am I supposed to hang out with? And your parents are like, literally everyone else, just not that person. Okay? Now, jumping over here for this example. Now, we know one rule we have in math is that we can't divide by 0. Another rule we have is you're not allowed to take, now this is a square root. A square root means invisible over here. We have an invisible little 2. So square roots have an invisible 2 in here, and the way you work with a square root, you might say what times itself equals this thing inside. The answer to a square root is always the product of something in itself. So something to pay attention to is your answer to a square root problem must be positive unless there's a negative out front. Also, you can't take the square root of something that is, fill in the blank, blank. Do you remember? You cannot take the square root of something that is negative. That means, so similar to how we set this one up, I basically said, okay, my denominator can't equal 0, let's solve from there. This thing inside is called your radicand. The radicand, spelled radicand. The radicand cannot be negative. So you basically can say my radicand must be greater than or equal to 0, and I'll solve from there. And that'll tell me what I can have. So it'll sort of be like that. So my radicand is linear. Again, being linear makes a lot of these things much easier. X plus 5 must be greater than or equal to 0, which means x must be, subtract 5 from both sides, greater than or equal, to negative 5. So this is your domain written as an inequality. Okay? inequality. I'm not spelling correctly. I get distracted, sorry. Inequality. Then I could also write my domain in interval notation again. So another option would be, so sometimes what helps people, let's actually do it on a number line first. Now I do this all day every day, so I might not need a number line, but just to help everyone else out. Here's -5, and you can be equal to -5, so there we are, equal. X is always read from the X, so even if X were on the right, read from the X. X has to be greater than or equal to -5, and greater than points this way, towards positive infinity. Keep in mind that that's positive infinity. So that's using a number line. And my domain, one more way, my domain, from the number line it's a little easier to do interval notation. When it's colored in, included, we use a bracket. So there's -5, comma, when do we go until? Forever and ever, until infinity. And infinity always gets a parenthesis because you can't actually get to infinity, okay? So there's my domain for that example there. Now we have two more examples before I kind of go up to this one. So two more examples right here that I'd like to go over right now. The next example is similar to the one we just did, okay? The main difference is that the radicand inside is not linear. I mentioned that having a linear radicand does make things less complicated, all right? Because when we solve equations, we actually use something called the zero product property, and we want the radicand or the factors to be linear. Now, the same rule applies for this, okay? We still need our radicand to be greater than or equal to 0, but the way we go about that is slightly differently. Because it's not linear, it bends quite a bit more. X squared minus 9 could have, subtract 1 from the degree, 1. We could have one turning point in our graph. And if we have one turning point in our graph, that means that we could end up above and below 0 more than one time. So if you think really hard, you should remember that this is something called a quadratic. A quadratic, when you graph it, makes a graph called a parabola. And a parabola has that U shape to it. It's really parabolic if you want to use the right adjective. Now, how do you find x-intercepts of parabolas? Well, you factor, and you set each factor equal to 0. Okay? Now, this is called the difference of two squares. So if I factor the difference of two squares, we should remember it factors using conjugates, x plus 3 and x minus 3. Now, it gets a little confusing if you try to say to yourself, oh, I'm going to set this and this, I'm going to put them both greater than or equal to 0. That is wrong. Okay? From here, you really just need the x-intercepts. If I set that equal to 0, okay, x plus 3 equals to 0, subtract 3, I'm going to get -3. That's something we've done a lot. And here, if I set x minus 3 equal to 0, I'm going to get x equals 3. Now, I'm going to kind of look at it like we have that number line right there. If I make a quick little sketch, just a tiny little sketch, okay? Now, you might learn more than one way to do this. I'm going to kind of show you the shortcut kind of way if I can. These are my x-intercepts. When you were in Algebra 2 and you learned about graphing polynomials, when you had factors to an odd degree, to an odd multiplicity here. See, the multiplicity is 1. They're not squared. They're not cubed on the outside of the parentheses, okay? These description words are very important that I'm using. First degree, third degree out there, whatever the multiplicity of each factor is. If it's an odd multiplicity, it cuts through the x-axis. And if it's an even multiplicity, 2, 4, 6, and so on, it's going to sort of kiss the x-axis and bounce off of it. Now, we don't know which side it comes from, but I'm going to kind of tie in the polynomial unit from Algebra 2 right now. Positive x squared. Positive polynomials finish pointing up. Their end behavior to the right is up. Now, really, if it's an even degree polynomial, like x squared minus 9 is, it will have symmetrical end behavior. Meaning if this side's pointing up, so is that one. Now, here's 3, which came from here, which was odd. Odd degrees cut through the x-axis. They end up on the other side. And then here again, an odd degree, so it's going to cut through. I have plenty of other videos where I talk about this. You can search for videos on polynomials in my playlist or in my archived videos. But this is in a nutshell what's going on here. So this is where it would equal 0. This is where it would equal 0. This shows me an area where my function is greater than 0. It's above the x-axis, my output values. And this I'm shown an area where I'm also greater than 0. My output values are positive, above 0. And then this area, from here to here, this domain, is where my output values are negative. So since my radicand has to be greater than or equal to 0, because I'm only allowed to take the even root of something positive, the x values that I want to use are going to be located where? They're going to be located from negative infinity until I can take the square root of 0, so until negative 3. They're not going to be located here. I know we're talking about x values, but this x is me crossing it out. They're not going to be there, and then they're going to pick up again right here, and they're going to go on and on and on until positive infinity. So the way you write your domain for something like this is capital D here for domain, from negative infinity until negative 3 with a bracket, because that is included, union positive 3 until infinity. Alright? If you had to write that using an inequality instead, okay? An inequality instead. Well, the way you would do that, and I'm not a big fan of that because it is more confusing to read if you ask me, I would say that x is less than or equal to negative 3, or x is greater than or equal to 3. But I think this is more logical. It goes from left to right. It's easier to follow than the inequality. Okay? All right. We have a couple more examples before we get to the main objective right here. The next example is similar to the first one. We have a rational means ratio. We have a rational function again, and the same rule applies as earlier where you're not allowed to divide by 0. This is not linear though, it's quadratic. As we just saw in the last example, sorry, that's my dog. As we just saw in the last example, when you have a quadratic, which is second degree, 2 minus 1 is 1, we can have one turning point, which means you can cross the x-axis more than one time. So if you can cross the x-axis more than one time, that means that this will equal 0 more than one time. So in order to find out when it equals 0, we're going to factor, set it equal to 0, and use zero product property, okay? All right, now factoring this quadratic, if you need practice on factoring quadratics, you're going to have to look that up somewhere else right now because I'm not going to spend time doing that. I'm going to start off by taking out, so again, negative x squared plus x plus 2 cannot equal 0. I'm factoring in order to solve. You would never bring over the 2 and take out the x or anything like that, okay? So factoring. I'm going to factor out or undistribute, use distributive property in reverse. X squared minus x minus 2 still can't equal 0. Then the negative is sitting there. I have x minus 2, and I have x plus 1. If I divide both sides by this negative over here, I'm still just going to have x minus 2 and x plus 1 is not allowed to equal 0. Then you use the zero product property. You're taking pieces of a product factors and setting them equal, or in this case not equal, to 0, because we want to know what will make it equal 0, because it's not allowed to equal 0. If that makes sense to you, I hope it does. So x minus 2 can't equal 0. That will happen when x equals 2. Therefore, x cannot equal 2. Get it? X plus 1 cannot equal 0. Therefore, that will happen when x is equal to negative 1. Therefore, x cannot equal negative 1. So, what is my domain for this example? I'm going to kind of show this in a few ways. For one thing, I can just write it like this as restrictions and call it a day. My domain is x cannot equal 2 and x cannot equal negative 1. I promise if you plug those in right here, it will cause my denominator equal 0, and your denominator cannot equal 0. Another way I can write it, or at least show it, I'm going to show it with a number line, sort of like before. It's just going to be a little weird looking, because here's negative 1. Make sure you always think about where you're putting your numbers. There's negative 1, which we can't equal. Here's 2, which we can't equal. And what is good? Everything else. Everything except those two numbers is fine and acceptable. So that's how you would visually show it. And better to me is the inequality. interval notation. So that means from negative infinity until negative 1, not including negative 1. Union, negative 1 until 2, union, 2 until infinity. Okay? So that's interval notation. Now, let's go up to the first example we had here. It's kind of a combination. So we haven't had one like this yet. So here I have a radicand, or a square root, or an even root. So my radicand, which is the 2 minus x, is not, has to be greater than or equal to 0. It's not allowed to be negative. Simultaneously, it's in a denominator, so really that means it can't equal 0. So if we're combining these rules over here, I guess let's keep this color for now, that means that this, the square root of 2 minus x, can't equal 0 because it's in a denominator, and it also means 2 minus x inside must be greater than or equal to 0. Now, how does this concept combine? The square root of what thing is 0? If I square both sides, if you want to algebraically support what we're doing here, you might say 2 minus x is not equal to 0 then, because the square root of 0 is 0. The only thing you can take the square root of and get 0 is 0. So now we're really combining these two rules, and this makes it a little bit better to look at because we're comparing the same thing. 2 minus x can't equal 0, and 2 minus x has to be greater than or equal to 0. So if one parent has this rule, you could only hang out with things greater than or equal to 0, but the other parent's like, no, you can't hang out with 0. All right, you have to satisfy both. That means 2 minus x has to strictly be greater than 0. Now, of course, they set it up this way because what do they want students to do? Negative x is greater than negative 2. Divide by negative, and everyone's going to forget when you divide by a negative, you flip your inequality sign, so don't forget to do that. Taking this over here. So that means divide by negative, x is less than 2. That's my inequality. Perfectly acceptable depending on how you're asked to give the answer. Here's my number line. Here's 2. Less than 2, so it's not included. Less than, we're going to go towards negative infinity. Right there. Interval notation goes from negative infinity until 2, not including it, with a parenthesis. So this is one way to represent an answer. This right here is another way to represent an answer. However, let's go back to kind of here for a second just to point out things that could go wrong if you find yourself in a certain situation. 2 minus x is greater than 0. If I decide to add x to the other side, you'll get 2 is greater than x. Make sure you don't graph that incorrectly. A lot of people will be like, okay, I need x, I need 2 on my number line, and they look at this as though it's a greater than sign, and they think, oh, you shade the way the arrow points. That's not true. Okay, if anyone ever told you that, they were lying. The only time that's true is if x is on the left and it's a simple inequality, sure, but if we have compound inequalities, or if we have x on the right-hand side, that's not going to be true. Read from the x. That's what I mentioned earlier. X is less than 2, and really give it some thought. If x is less than 2, that's how we shade it. So to avoid, you could make sure you get x on the left, but are you going to forget to divide by the negative? Well, you got to know yourself. Either way, these are all the same answer. So if I write a nice sentence, the domain of the function, here's my function, g of x is equal to 1 over the square root of the quantity 2 minus x. The domain of the function consists of all real numbers. Now, all real numbers symbol, in case you ever see it, is this r with an extra bar in it. All real numbers x. X is some variable input value. Variable, the first 2 syllables vary, means it can change. Where what? Well, where x is less than 2. That would be fine. Where, maybe you write some other fancy notation, x such that x is in the interval negative infinity to 2, but that's totally fine what we have written right there. Okay? So that is a quick little lesson and explanation on domain.